Ranty Flat Earth.
Yes.
Guest, how you doing? What did you want to present?
I had a little something for you guys. Might have presented it a little bit before, but just a bit more concise this time. If you've got 5 minutes to bear with me.
Yes, we absolutely have. You're presented, you're on screen, you're full screen, you're looking good.
Okie dokie. Right, okay. So the first thing I want to talk about is the curve calculator, because I know you guys hate using the curve calculator, but this is important because the Globers always want you to assume that when we're talking about the curve calculator in regards to a flat Earth, we always have to assume that it is sea level. You know, so this little dotted line is denoting flat, the water lying flat, because that's how they always want things to be. They want it to be measured, you standing next to the water, your height above the sea level, and that's it. So if you're stood by the water, your toes are in the water, you've got your tripod set to 4 feet, they want you to input 4 feet into the curve calculator as your height above sea level. And I'm going to show you how that's incorrect. And that's down to a host of things, including not only just the wave height, but the swell. And to give you an indication of that, this is the formation of your normal waves, where you have a trough and you have a peak. So you have the amplitude, which is higher than sea level. Now, the amplitude is always half the wave height. And wave heights can be calculated due to a number of different things, not just wind, but also the swell on certain days. So if we go to, this is the Hawaiian education.edu. It's the University of Hawaii. And this is on their page over here. I've taken this image. There's lots of different images very similar to this, but it's exactly as it's meant to show. This red line is denoting sea level. So I'm going to show you a couple of images that I've put up here. And this is called the amplitude of a wave. And what we're going to look at here is if your camera is sat on this red line at the beach, and then you're looking out to sea, what you have is you get peaking waves, you get swell, you get the breakers. Well, essentially, all these things are blockage higher than where your tripod is. Your tripod feet will be lower than the breakers, the peaking waves, and the swell as you're looking across water. And these can be measured by the WMO sea state code. And that's a combination of the wind and the swell. So within WMO sea state code of, say, 3, you get between 1'8" to 4'1" inches of wave height, which is equivalent to around about 2 feet of blockage. So if you had your tripod set to 4 feet, essentially you would have, up at the top here, you would have 2 feet high waves in front of your direct line of sight over a constant area. So essentially, when you put 4 foot into your curve calc, that would be incorrect because you're having to look above the waves. The waves are now the surface because they are 2 foot in height and they are constant across the whole length. To give you an idea of some of the wind speeds in this kind of thing, if we go into knots and we go to 20 knots, which is a moderate sea state, we can expect wave heights of between 1.25 and 2.5 meters. So 2.5 meters, 1.25, 2.5 meters, we've got 4 foot of blockage to 8 foot of blockage. And that's just in a moderate sea state. Back up here again, if you'd set your tripod to 4 feet with your camera set right on the shore, like right where the water's lapping up, in a moderate sea state, you would have 4 foot waves in front of you. The height above the actual sea level would be 4 feet. Your camera will be set to 4 feet. So essentially you would be looking straight across from zero, from literally zero. And that's not including the white caps that happen when you get a speed of 22 to 27 kilometers per hour, which isn't that strong really. So when you get a wind speed of about 15 miles an hour, you start to see white caps on the top of these breakers and the peaking waves. Then you also get the spray that's being kicked up above these waves and when they're breaking. So if you have your camera set to 4 feet, you're not only looking through sea level, which is now level, but you're looking through all the spray and everything else that goes with it. To give you another indication of, this is how the globers would like you to present yourself. If you're looking from point A to point B over a body of water, they want you, like I say, to put your elevation where your tripod feet are next to the water, above sea level. Not taking into account all this obstruction, these waves right here across this entire section. So I think it's incorrect the way they've tried to trick us into calculating this without taking into account the sea state. One last thing I want to talk about is something called wave shoaling as well. And this is taken from, where's it taken from? Let me just bring it up so that you, wave shoaling. So this is taken from wave shoaling here on Wikipedia. If we go back to the image, I'll just read it off what it says. It says, in shallow water and parallel depth contours, non-breaking waves will increase in wave height as the wave packet enters shallow water. Now, to give you an indication of where that might happen, we go over to Rottnest Island, because there's been a few images taken from Rottnest Island. And what we've got here is we've got like a line of sight out to some deep water. So across this ledge here, we've got an elevation drop of around about 50 to 60 meters in total over this 15-mile stretch. But then up this shelf here, this darker area is where the shelf starts. And just at this point here, we're already down to nearly 600 meters in depth. So in a space of, what are we looking at there? In a space of 6 miles, it's gone from 600 meters in depth to 60 meters. Now that is what you call a shelf. So when the tide's pushing in, it's literally doing exactly what it's going to say on what happens with wave shoaling. In shallow water and parallel depth contours, which is this, non-breaking waves, which means it will just be a raise in the water level, will increase in wave height as the wave packet enters shallow water. So I'm just going to put a little indication of what that would do to your boat here. As the water's pushing in and it's starting to shoal, you're going to get some increase in height in these areas here as the water's pushing in. And that is going to be blockage from you trying to view it from the shoreline. And if you're looking at a boat and you're asking, why do things disappear from the bottom up? Well, if it's shoaling in these areas, this is what's going to happen. That boat will be hidden behind this shoaling as it moves in from the deep into the shallows.
Cool.
Okay.
Is that the end of your presentation?
I agree with that.
It is.
That's superb. Cool. Thank you very much, Ranty. You staying at home and obviously thumbing through the Google pages is yielding as many rewards as you being out and about with your camera. Excellent.
It sure
Thank
is.
you. Thank you very much for that.
No worries.
Have you done it as a presentation, Ranty, on your site?
I could cut it out, I suppose, and upload it onto my YouTube channel.
Yeah, do it.
So the curve calculator doesn't account for perspective or height of waves now.
The way it doesn't know. And what you'll find is that the amplitude of the wave is the most important part. So the amplitude is always half the height of the actual wave height. So you can check it out. You can go anywhere. You can look at what the wave heights were for a certain area at a certain time. And you can get an indication of what the wave heights might be just by the speed of the wind. So for instance, if you've got like I said, a 20 knot wind, you can expect up to 8 feet high waves, which means that you actually get 4 feet of obstruction. 4 feet of obstruction. And this is calculatable. I think the guy that did the towers, what's that spiral tower? I don't know. He got in touch with me anyway to analyze this particular tower, Turning Torso, I think it was called. And basically, he was filming in rough conditions, and he was filming in rough conditions. In his most distant images, his height above actual sea level that he was quoting was just between 7.9 feet and 9 feet in total. Well, in these rough conditions, these wave heights were already 13 feet. So he hadn't taken any of this into account at all, and all the spray, all the caps that were going off at the top, none of this, nor his camera. But it was interesting to note that he thought he was actually 8 feet above sea level, and didn't think that the wave heights were very high, because it's really difficult if you're zooming in, say, to 15 or 20 miles away. It's really difficult to actually gauge how high those waves are, because you can't perspective at those zoomed in distances. So it's good that you can actually check out roughly what sort of heights of these waves to expect under certain conditions. And as I say, the swell adds to the height of the waves as well. So this is just in speed, you know, this is just the wind speed to give you a possible wave height. Now, this is just, this isn't even taking into account the sea swell. This takes into account the sea swell.
It would be good in your presentation if you put that diagram on there, and if you also added a camera on the other side of the water, and to say that if your camera is looking at the other, if you put a little camera on the other side of there, but do it more to scale, because those sea waves are supposed to be 4 foot. So the camera should be like half the size, well, less than half the size of that one on the other side. So you can say, well, we won't see the camera on the other side of the shore, not because of curvature, but because of the waves, which is documented on this site.
Yeah, and one other thing I would like to say is that they also state that whatever the significant wave height is per area. So let's suppose you wanted to find out what the significant wave height was for Rottnest, and they said it was 2.5 meters. What they also say is that 1 in 8 of those waves will be higher than the significant wave height given. So even if it says it's 2.5 meters, 1 in 8 of the waves will be higher than that. So, and that's just one wave, and obviously you've got hundreds of waves over the ocean. So essentially what it's saying is that even though they quote 2.5 meters as the significant wave height, you can normally expect the whole ocean to be significantly higher than that, because you'll be looking across not just 8 waves, you'll be looking across thousands of waves.
There's one more point. Hopefully it'll be on your trimmed out, but we'll see. If you don't like it, then tough luck. If you can just go back to your picture that's just the picture of the camera with the waves and the 2 shores.
Yep.
Perfect. So this is, for those who are unaware, being presented in Muppet vision, otherwise known as orthographic view. And what this also does is limit the effects of perspective by basically ignoring them. So the right hand side, I'll do it in my mouse so you can't see it in the Hangout unfortunately, but the right hand side is the same physical size in this depiction as the left hand side. So if we had 2 tripods, one on each side, they'd be the same size. They'd appear to us in this picture the same size, whereas in reality this tripod is your viewing position, and if you were looking at the exact same size tripod, it would be smaller by virtue of perspective on this side. That's why they put the curve calcs and the way the maths works in the curve calcs in this view, to negate perspective. So in other words, you can give this, let's do it with the waves, because that's what you're doing, right? Ranti said these waves are 4 feet. Well, they're 4 feet there, they're 4 feet there, and they're 4 feet there. But in reality, the closest to the shore has the biggest angular size. So when you're looking at it in terms of your angular view, which is how we view things, the closest wave makes up the biggest angle, and therefore potentially, if these were all, in quotes, 4 feet waves, the closest 4 foot wave would have the largest angular size, obviously getting smaller as you got further away. Moreover, the thing you're looking at, in this case, if there's a tripod on this side of the shore, that is a considerably smaller angular size. Therefore, even though the tripod might be 6 foot, the 4 foot wave in the near foreground will obscure the reduced angular size of the tripod on the other shore, all of which is ignored by putting it into Muppet vision, or orthographic view as it's known, because all of the values can be given in a feet and inches value rather than an angular size value, which is how we see things. We never get to see the tripod, we see the picture the tripod makes, or the camera. Anyway, that's my little 2 pennyworth at the end, Ranti. Excellent presentation.
Well, just one last thing, I just want to show you what effect that would have on the curve calculator, which is quite important, because very often the Globers will always say that falls into standard refraction, it's not a problem, because what people will quote is their height next to the water with their toes touching the water and given a height above sea level. So if they're given a 6 foot height above sea level, distance 20 miles, let's just go for geometric hidden, because 192 feet hidden, right? But what happens when you actually factor in the waves and you realize that your camera is set to 6 feet, but the wave height obstruction in front of you is 4 feet? That literally means that you're only looking, your height above the actual waves is only 2 feet. So when we put that in, it goes from 192 to 222 feet of drop. That's 30 foot of drop, additional drop now that the globers will have to incorporate into more refraction to get around this point. That's the point, because us putting a 6 foot height in above sea level isn't correct. It should be 2 feet or so, or it could even be 0. And I'm sure there are times that the wave height will actually be higher than your tripod at the shoreline. So it's just the way it is. And I think people need to take this into account. It's certainly bad for the globers because standard refraction doesn't account for this. This is going to change every observation from just standard refraction. It's going to have to be superlumin refraction, as Rumpus would say.
Well, you've got it on screen, just to add a couple of things. So in the actual calculation, you can see it here at the top. It says actual radius. So this calculator, the entire thing's a begging the question fallacy. It's automatically assuming the outcome. There it is. You're not measuring anything. You're assuming your outcome. Oh, there it is again. Radius, where they smooth out and flatten out the plane that we actually see when they hijack perspective. And if you can scroll down, just last but not least. So when I was talking about Muppet vision, oh, what a shock. Here we are again in Muppet vision, seeing the side of our own head. And what does it say next to it? Eye, camera. No. We never see the camera or our eye. We see with our camera and with our eye. We don't look at the side of our own head when we make observations. But just like in Ranty's picture that was in Muppet vision, we have an observer and a target that will remain the same. Sorry, if you stay on the calculator, if you would. So we have a target and an observer that do not change with distance. It doesn't matter how far you put this between these two dots. It doesn't matter how far around you move it. The feet and inches value always remains the same, even though it's getting ever smaller as you move it further away from the observation position. But by putting it in Muppet vision, you remove all aspects of perspectives, and you can tell by the way they ask you for the whole number values and not the angular size values. So in Walter Bislin's calculator, it can give you an output in angular size, but you'll still be putting the whole numbers, the feet and inches, the actual sizes through the calculations, and the way the maths works is identical to any other curve calculator. They have to be, because if they contradicted each other, they'd have a big problem. They all must work on the same formula. They all do work on the same formula, and they all do the same thing. Remove any aspect of perspective, the idea of objects getting smaller with distance, which they absolutely do, by giving you this side elevation that will not change the actual effects that you see. Things get smaller with distance, and they replace it with this bullshit, the curve, and say that the reason this is getting more and more hidden is because there's more and more curve, as opposed to it's getting further and further away and getting smaller and smaller and smaller, and the bottom of it, with the most reduced angle, will disappear first as a result of things getting smaller with distance, otherwise known as perspective. So that's a summary of why we call this the begging the question, because it's assumed its outcome, it's already got a radius. Proof of nothing, because it's begged the question. Perspective hijacking, because it's in Muppet vision. Curve calculator. So that's why we call it the begging the question, proof of nothing, perspective hijacking curve calculator, because that's exactly what it is.
Would now be a good time to tell you that I've done a GoFundMe.
Yeah, you can plug your GoFundMe. You can strap it onto the end of your snip out then, can't you?
There we go. I want to get a drone. Essentially, I'd like to get a drone to help with the studies this year to go with the P1000. So if anybody wants to try and help out in this particular cause, I know you did it with the P1000 last year, but I'm sure that you'll get plenty of use of the drone if people are willing to help in this particular endeavour.
Sure, we'll do another Ranty-a-thon on your channel if you like.
Sure, why not?
That worked well last time. So last time Ranty basically played a load of his footage, showed what he's done to date, and I spammed the chat asking people to contribute to his GoFundMe campaign. So, you know, I'd love to do that again. That was great fun. I like the Ranty-a-thon because we got to see loads of footage from you. So I'm well up for that if you're up for it.
Sure, sounds good.
Cool, we'll do a Ranty-a-thon soon. Watch this space.
Not today though. Not tomorrow. Maybe Thursday, Friday.
But feel free to spam the link. It's an active GoFundMe, so if you want to stick the link in, I'll approve it. If you want to put it in the chat.
Okay. All right.